Okay, here's a problem. We want to calculate how long it takes a spacecraft launched from the Earth to reach the planet Saturn. It's a good problem because it makes use of Kepler's third law that we've talked about in class quite a bit. But it also connects with a real event. The Cassini spacecraft was launched in 1997. And it's now presently exploring Saturn. But how long did it take to actually get there? So let's work it out. And of course, the crucial thing is that we want to use the tool that we have for this, which is Kepler's third law. Okay, that's a big deal. And of course, Kepler's third law, you all know, p squared is equal to r cubed. And in this situation, what we're going to do is start off with a knowledge of what the size of the spacecraft orbit must be. And we want to find this. We want to find the period. That's the goal. So let's take a look and see how we would do that. And as we've talked about before, the first thing you've got to do is you've got to have a good drawing of what this looks like. So let me make a drawing here, and there's the Earth's orbit. Okay, and here's the Sun at the middle of the Earth's orbit. Okay, and somewhere out here, almost 10 times as far away, my drawing isn't going to be so great, but is Saturn's orbit. You get the idea. Okay, so here's Saturn out here. If we look at the distance from the Sun to Saturn, we can look up in a textbook or something, and we did find out that was 9.5 AUs. That's the semi-major axis, the orbital radius for the planet Saturn. And of course, look, filling in this picture, we know that the distance of the Earth from the Sun is 1 AU. So what's the most efficient orbit that we could take? Well, it's called a Hohmann transfer orbit, H-O-M-A-N. Talked about it in class. It's an orbit that starts at the Earth's orbit, goes no lower than the Earth's orbit, steadily climbs, reaches Saturn's orbit, nudges Saturn's orbit, goes no higher, does not cross it. So it's an orbit that's going to be an ellipse with the long axis of the ellipse. Here's the orbit. It's going to be like this. Going to nudge the orbit of Saturn. I'm going to draw this part in dashed line, because the spacecraft, of course, doesn't come back. We launch it, it goes from the Earth. So here's the Earth right here. That's the Earth at the launch, at the launch of the spacecraft. Here is Saturn at the time it reaches there, but of course Saturn was not there when it was launched. So here's Saturn. And as we can see, what we're going to do is we're going to put the spacecraft, let me draw a little bitty rocket right here, and we're going to orient the rocket in this direction. Okay, there's a rocket. There's the nose of the rocket right here. Here's the tail. We're going to fire the engine. There's the exhaust coming out of the engine so that it picks up speed. And it's going to steadily climb, getting higher and higher. It's going to travel along like this, getting higher and higher the whole time. But also it's getting further and further from the Sun, so it's going to slow down. And it's going to reach Saturn when it's actually slowed down substantially by the time it gets there. So we can put this knowledge together, and we can see that the orbit of the spacecraft is going to have a long axis, a major axis, is going to be 9.5 plus 1, going to be 10.5 AUs. Okay, and then we can right away figure out the thing we want to know. That means the semi-major axis, SMA, which is the same, we've often called it R, and that's going to be half of that. That's going to be 10.5 divided by 2, so it's going to be 5.25. Okay, now it's real easy to just apply Kepler's third law. R cubed going to be equal to p squared. R cubed is going to be equal to 5.25. We're going to cube that thing. When you do that, the number that you get is 145, and that's going to then equal p squared. Okay, so if we want to find p is going to be the square root of 145. Now the square root of 144 is 12, so it's going to be just a smidgen more than 12. Let's just say that it's 12. And of course the units of that are going to be years. And then you have to stop and say, well, what have we found out? We found that the period of the spacecraft following its entire ellipse around, starting at the Earth, going up, getting to Saturn, and then going back, which we don't want to do, would be 12 years. So obviously the travel time is going to be half of that. You only want to get there and you don't want to come back, so it's going to be 12 divided by 2. It's going to be equal to 6 years. And that's what we want to know. That's the answer to our question. Now, let's look at what's gone on in this interval. We started here, the spacecraft and the Earth. The spacecraft came from the Earth, so it was beginning its journey with a speed of 30 kilometers a second around the sun. And you can work out that in order to get it to Saturn, you have to give it a speed to begin with that's greater than the Earth's circular velocity. And it's in fact got to be 40.1 kilometers per second. That's the speed it has to have to start here and to move into this elliptical orbit and begin to climb. Gets out here, it encounters Saturn. Now Saturn doesn't move that fast in its orbit. Saturn moves along at about 10 kilometers per second, 9.7 exactly. But the spacecraft has slowed even more than that. It's gotten down to about 4.2 kilometers per second when it reaches Saturn. So you have to fire a rocket to put it into orbit around Saturn. We're going to leave all that stuff out, but that has to be done. So if we look back and see what was going on with Cassini and what was that like, well, it was launched in October of 1997, and it reached Saturn. The date that it reached Saturn was June 30th, 2004. October to June, so this comes out to be about 6.5 years. So our answer was pretty good. Now, what was going on in this? And Cassini is a complicated spacecraft. We've left out a lot of stuff, but en route from the Earth to Saturn, in order to save rocket fuel, which is incredibly expensive, Cassini used something called the gravitational boost. It went past Venus twice, came back a second time to the Earth. Each time it got a little kick from the gravitational field of those planets. It then passed by Jupiter, got another kick from Jupiter in December of 2000, and then it cruised the last 4 years until it got out to Saturn. So each time Cassini passed by those planets, it got a little gravitational kick, kind of like hitting it with a bat when it's a moving baseball, and picked up a little speed, and that meant that we did not have to spend $20 billion to get it out there. We only had to spend about $1 billion to get Cassini there.